some of the popular or well-known large language models. Some would argue that the BERT model is not really super large, but it is what kicked off, you could say, this exploration into the large language domain. So what makes large language models different than, let's say, a language model or any other model? Well, it turns out that language models which are particularly large exhibit emergent abilities. And what we mean by emergent abilities is the ability to solve complex tasks that is possible only with large models, but these abilities are diminished or not observable in smaller models. Again, by smaller, I mean like smaller in the number of parameters. So on the right, we have like a depiction of a multi-layered perceptron, which is like a very basic neural network. And a parameter is essentially an arrow in that diagram. And the arrow is the arrow in simple terms corresponds to like a value with which is the strength associated between like an input and the output or the neuron it's connecting to. So when we talk about parameters, we are talking about the number of arrows in the model. And simply put, it could be like a floating point value, or these days it could be even integer values. So how do different large language models stack up? The first large language models per se, like BERT and GPT, have like hundreds of millions of parameters. GPT-2 has billions. And as you can see, as the years have progressed, the models have moved into the higher billion categories. In comparison, our human brains has like 3 orders of magnitude more parameters. It might not be a fair comparison because here, by parameters in the human brain, I'm simply referring to the synapses, which is like the connection, which is synonymous to parameters in a neural network. So moving on. All right, so I touched upon emergent abilities, right? I think it's an important concept to discuss when we talk about large language models. And simply put, emergent abilities are abilities, or is an ability in large language models that do not exist in smaller models. So an ability that is observed when you train larger language models. So what's unique about emergent abilities? It turns out that they just pop up. So you train a model, you train a bigger model with potentially or likely more data, and you keep training bigger models. And there comes a point where these models exhibit or are able to solve problems that were not solvable by smaller models. So for example, on the figure on the left, you see tasks such as modular arithmetic, word unscrambling, multitask natural language understanding, and many more. And you see, and on the y-axis, you see the accuracy, which is the model performance. And on the x-axis, you see the amount of floating point operations used to train the model. So higher floating point operations would mean it's a bigger model if the training data remains the same. And so you can see that at certain points in the graph, there is a spike in the performance. And that's when we say that these models are exhibiting emergent properties. And if, let's say, you were to observe linear improvement in performance, right? And so you would think that maybe I could plot a linear, maybe I could fit it with like a linear regression model to predict what the model performance would be at, let's say, if I give it X amount of compute. Turns out you wouldn't always be right, because as you can see in certain cases, this linear relationship is kept till a certain point, and then the slope of the relationship changes. And so it's more like a piecewise function in this case. On the right side, on the figure on the right, we look at emergent properties, but emergent properties that are exhibited due to certain training techniques. Let's call it that. So chain of thought prompting is pretty popular these days, and it corresponds to asking the large language models not to just solve problems, but solve problems and think step by step. So that's something that's commonly used. So what would that mean? So if you're solving a math problem, you wouldn't just present the model with a linear, let's say a quadratic equation, but you would also prompt it with something like solve this problem and explain step by step. So it turns out that this explain step by step does induce some sort of emergent abilities in large language models. And so, and then moving on, there's also instruction following. So you can, instead of asking the model to just complete the text, so you provide it maybe an initial seed text, and then you ask it to complete the text. Like instead of that, maybe if you formulate the problem in the form of an instruction where you say the following is blah, 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 like maybe summarization task, and then you ask the model to, and then maybe you collect human written, human generated outputs on those instructions and train the model in supervised manner, you see again the emergence of emergent abilities within large language models. And similarly can be seen across different graphs. So this is like an important characteristics of language models. And yeah, so let's move on. So I wanted to also cover potential reasons why large language models have picked up in the years, and what are some of the important components or criterias that enable adoption of large language models. So this is a well-known fact, and even before we had the shift to larger models, we knew that deep learning models and neural networks scale well with data. So generally, traditional machine learning models, like they plateau with training data. Now, this is not true for all tasks and all data sets, but this is generally true across multiple, at least complex tasks. But whereas with neural networks, and you can essentially get better performance with more data in a lot of tasks, whereas the traditional ML models again plateau. And so I'm sure some of you have also heard saying that neural networks are universal approximators, right? And so what that essentially means is that they can model any function, and with enough data, you would be able to train a good enough neural network for most tasks. So this is, I would say, like one reason. Moving on, like clearly there has been a surge in the amount of training data available for these models. Like we produce a lot of data every day, and through social interactions, maybe not all of it is text, but even if 0.1% of it is text, it's still massive. And the internet user base is always growing year on year. So we are continuously producing more data. And that's an important sort of contributor into obtaining data to train these large language models. So on the right, you can see a table with some prominent data sets and what their size roughly approximates to. Now, most large language models use a combination of these data sets in different proportions. But I guess it's important to know what the scale of data that's used to train these models are. Additionally, there's also the accessibility or availability of open source tools or platforms, whatever you might call it, that enable easy sharing of data, right? So you have like Hugging Face data sets, which provides easy access to plethora of data sets. There's also Google Data Search, which you can use to find data sets that interest you. There's also, for folks who have been in ML for a few years now, would also recognize the UCI ML repo, which I don't think most people use now, but it was also an important contributor to data sets previously. So that's factor number 2, in my opinion, which is like availability of massive data sets. So we did talk about the availability of massive data sets, right? But there's one issue with these data sets. It's that they are not labeled, because to solve for any meaningful tasks, we probably need labeled data, right? So for example, to build an NER engine, named entity recognition engine, you would need data to explain to the model how to perform NER. And so that's supervised data, that's labeled data. Whereas all of the data that we just saw, or the data sets, were unsupervised or unlabeled, sorry. And so how is it that we're able to train these large language models to solve any of our tasks then? Well, it turns out we do have supervised data, but it's only a fraction of the data that we have. And an important contributor to the functioning of large language models these days is the ability to train on unlabeled data. So we have certain popular, I would say, pre-training objectives. The reason we call them pre-training is they're done before the actual training process, which you could call the fine-tuning process. And so pre-training essentially allows the models to use unsupervised data to learn parameters that can enable transfer learning. So transfer learning is the ability to move around from one task to another. So pre-training is like, let's say if you have a lot of data, but it's not labeled. So you can use certain pre-training objectives such as mass language modeling, which is like fill in the blanks, which is shown on the, like I said, diagram on the left. And then there is like prefix language modeling, where maybe you provided a piece of text and then ask it to complete the text. So these are two popular pre-training strategies. And yeah, using these strategies, you can maybe initialize the model parameters that we talked about in a better way, or you can put them in a better state so that they are more optimized for the fine-tuning part, instead of initializing your weights from random and then just fine-tuning on those weights. So there's the idea of self-supervision or pre-training is pretty important in my opinion, and is another contributing factor into why large language models work really well. Again, when we talk about large language models, you can't really forget or not talk about the transformer architecture. For those who are aware, the transformer was a paper that was, I think, in 2017, and attention is all you need, and the name of the paper. And it was pretty popular because it introduced a new paradigm in learning language models or learning from text. So previously, I think we're all aware, there were models such as recurrent models, LSTMs, RNNs, so on and so forth. They had multiple challenges in training, and turns out they didn't scale too well with data, and they didn't perform really well on larger texts. Transformers, the idea behind transformers is pretty simple. It's essentially paying attention. And if you think about attention, it's like paying more attention to certain parts of the text per se than the others. And this is important because when you think about language or any tasks associated, let's take translation, for example, like to properly translate from one language to the other, you don't really need the entire context. You don't really need the entire, if you have a 1,000-page book, you don't really need the book to translate. You just need a few words surrounding the word that you need to translate or the sentence you need to translate. So attention enables that by allowing the model to pay or to enhance some part of the input while diminishing the other, in simple terms. And these models or transformer models with attention can be parallelized because of something called positional embeddings. I do not cover the architecture in detail here, but the idea is to get rid of recurrence, because recurrence is a bottleneck for parallelization. Because when you consider text, right, you can't really look at the second word in a sentence before you look at the first word in a sentence, right? That's the idea behind recurrence. Whereas transformers introduce this concept of positional embeddings, where you can parse them or process the output or input in parallel. So this is where GPUs come in, right? So that's my next point. Like, compute is getting better, and graphics cards are getting much more powerful these years. And there's a lot of innovation both on the hardware as well as the software side. So the CUDA libraries and so on and so forth, they're being optimized constantly, and which is leading to significant improvements and allowing us to train even exceedingly larger models than we could previously. So there are probably a lot more factors that go into why LLMs are popular and why they're rising, but I would say like these are a few important ones. Okay, moving forward, I think we can transition into maybe a little more technical part of the talk, where I want to talk about architectures and certain prominent LLMs. So to begin with, what are the different architectures, right, that are commonly used? So it's actually pretty simple. Like we have an encoder architecture, a decoder, and an encoder decoder architecture. So we have models that are encoders or decoders or encoder decoder models. So the first model, or one of the first model like BERT, right? It's an encoder only model, which is it learns, it takes in inputs, and the idea is to learn better representations of the input. You would have heard of the term like embeddings. So it generates contextual embeddings as its primary task. And it uses mass language modeling. Yeah, so maybe let's just talk about encoders first, right? So what is the pros and cons of encoder? Well, it turns out that encoders, at least on a smaller scale, perform really well on NLU tasks. So NLU, or natural language understanding tasks, is the task of our tasks such as NER, classification, anything that does not require generating text is an NLU task. And so these tasks are pretty well suited for these models, especially at at the scale of BERT. It turns out that encoder-only models perform reasonably well on these tasks, and they're more data efficient simply because they're not generative in nature. They're discriminative models. And so that's the encoder side of things. So what about the decoder? So decoder is slightly different. In decoder, the idea is to uh, is to uh, do next word prediction or complete a sentence per se in simple terms. And how a decoder does this is that you provided maybe a seed sentence or like half a sentence or phrase, and then it tries to complete the rest of the sentence. So if you think about it from a pre-training standpoint, you have enormous corpus of text with hundreds of lines, maybe from Wikipedia. Maybe you give it the first couple of sentences and ask it to complete the sentence. So this is like a pre-training objective, and this is how decoders are pre-trained, which is in contrast to mass language modeling, which is more of a fill in the blanks task, as we saw before. So decoders are good in the sense that they're generative models. So generally speaking, they're good on generative tasks such as summarization or better. And encoders can't really be used in, let's say, abstractive summarization, right? Because in abstractive summarization, you want to generate or maybe even sometimes paraphrase the summary, whereas encoders can only be used for extractive summaries. So you can extract sentences from a paragraph, but you can't really generate new sentences. So that's the decoder. And then there is the encoder decoder architecture, which is like combines the two. And where are these used? So some popular models are like BART and Plan T5 models, which use the encoder decoder architecture. Here, the objective is mostly similar. Like you could even combine mass language modeling with next word prediction in these models. If you look at the UL2 Unified Learning Paradigm paper, it talks about different ways in which you could denoise, like you could corrupt spans, you could do next word prediction as well, and you could do something called extreme denoising, which is like corrupting spans in a text, but corrupting a lot of spans, or in an extreme manner in which it's hard to reconstruct. So these are different pre-training objectives. So one would think that encoder decoders are probably the best of both worlds because they combine the encoder and decoder simply. Turns out that like most of the top performing models, at least the ones that I have seen, are in decoder only. And I think at scale, at very large magnitudes where you have a lot of parameters, it probably doesn't matter if you use an encoder decoder model, because both are generative models, and essentially both both are generative models, so they generate text. So when you talk about large language models these days, you would not find any large language model that is, or you would generally not stumble upon encoder only large language models, because their utility is limited to just discriminative tasks, whereas you want to generate text. And so GPT, Chat GPT, all of these are generative models, and so they are decoder models, or they have a decoder. I think there's probably a lot more to cover here, but I'll move on. And I will move on to maybe like the more so this is what I wanted to primarily talk about, like the evolutions of LLMs. How do we reach let's say GPT-4 currently, where did we start off from? So like, I would like to obviously start off with BERT, right? Because it's the first transformer, it's the first paper which showed that uh, pre-training like mass language modeling is super useful when you have a lot of with transformers and when you have a lot of data. They in fact achieve state of the art on a lot of NLU tasks. I say NLU because they're not generative, they're discriminative tasks, such as classification, so on and so forth. So that was the first, I would say, like breakthrough in NLP when it comes to like kicking off the large language model paradigm. You know that below that I have mentioned GPT-2, which is so this is the predecessor, no, successor of GPT, and why is this one important? I feel like this one is important because it showed that you could essentially do something called zero-shot transfer, which means that let's say if you only trained on supervised data sets, or sorry, only pre-trained on unlabeled data sets, and then you ask the model to perform zero-shot or perform zero-shot reading comprehension or translation, it does all right. Like it doesn't do poorly, especially for the time, because you would generally expect supervised models to outperform all models that are trained or perform zero shot anything, right? Because zero shot means they haven't seen training examples. And so in these cases, you can see apart from summarization, GPT-2 shows that like larger models do better without like external supervision. And so this is like an important insight into large language models, because the largest model here is like 1.5 gigabytes, which is still considerably lower than, let's say, Chat GPT or GPT-3. But it showed that there's a linear correlation between model performance and the number of parameters. So this I think sparked interest in training even larger language models, because then who knows, a linear relationship might continue, and then you might end up with models which are optimal or which can even beat supervised models if the trend continues. So moving forward, yeah, I'd like to discuss the T5 paper, which is like unified text-to-text transformer is what they introduced. So this work is unique because I feel like it was probably one of the first that introduced a framework that converts all language problems into a text-to-text format. So here the approach is you pre-train again, but what you do instead is, instead of doing supervised training for each task, so let's say we're trying to solve for 5 tasks, right? You would maybe pre-train the model and then create 5 different copies and then train them in a supervised manner for other data sets. In this paper, the idea that was introduced was that why don't we translate all of our tasks into generation tasks? So for example, if you want to do translation, you can look at the example in green, which says translate English to German. And you could do it with a decoder or an encoder-decoder model only. And you could essentially convert all of your data into from format A, like if it was like a classification, right? Generally, you want to predict labels. But instead of predicting labels, why don't you use the decoder, or why don't you generate the labels? So it's like predicting the next word instead of trying to classify the next word. So the paradigm here is generative. And what you can do is with this paradigm, you can treat all tasks as task generation. Even LNU tasks can be treated as tasks that can be solved using generation or next word prediction. And additionally, this paper also introduced the C4 dataset, which is the colossal common crawl dataset. It's a few terabytes, and I think it was an important contribution in that sense. All right, so this paper essentially, introduced a way in which you could solve all problems, even NLU problems, as generative problems like next word prediction. Yeah, please.
So the last one, the T5. So the model needs to know what the task is by reading its input. So was that supervised trained as well?
So there is still supervision here. The pre-training part remains the same. It could be mass language modeling or next word prediction. But when you come to the supervised part, previously approaches were like, I would pre-train on a big corpus and then I would fine tune on this data set, right? But what this paper, or one of the first ones to propose, was that why don't I train in parallel on all tasks? So my model is multitask per se for all the tasks.
So here it says
Yeah.
summarize on the blue box.
Yeah.
So it's asking the,
Yeah.
it's able to do multitask.
Yeah. So think of a supervised, think of a labeled data set for summarization. And instead of training just one model for summarization, you train summarization along with all other tasks. And
But the user gives the tag, the task tag.
yes, so these are generated using certain templates. So for summarization, you would have like summarize and then a placeholder for an article, and then TLDR or summary, and then the model has to predict what comes next.
So
Yeah, it's templated basically.
still a few steps before the current.
I would say it's getting there. Yeah, because this is what you want, right? Like if you have tried out ChatGPT or something of that sort, like you just ask it to do X and then it does X. So it follows instruction.
But there it knows the task it needs to do. Here, like we're saying summarize and then.
Yeah, there also you would say something like summarize the following article, right? Yeah, in this case, you're just saying summarize. So I would say it is synonymous, but the idea shifted from task-specific fine-tuning to fine-tuning for all of the data sets. And yeah, and then let's go on to the next one, which is the GPT-3 model. And this introduced the main contributions, I would say, is that they went from 1.5 billion parameters in GPT-2, which should promise, as you were increasing the model size, the performance was increasing. They went to like 175 billion parameters. And as you can see on the graph in the middle, performance on 0, 1, and few short also increases. So it's like you pre-train a larger model on more data, and then you see the 0, few, and 1 shot performance go up. Which is just an extension of GPT-2 in that sense. What I find more interesting is also the graph on the left. So on the y-axis, you have the validation loss, and on the x-axis, you have the compute used to train the model. And if you observe the curves, so each curve is different model parameters. The lighter curves are like more model parameters. So you can see that there is some amount of convergence when with models up to a certain size. But if you see the last curve, it achieves a much better loss. So this further confirms or validates the hypothesis that the larger models you train, with optimal training data, that's a condition, you would probably obtain better performance. Also, this also depends on data quality and other factors, but this is a general conclusion you can make. Another interesting insight of this paper was that it was probably like the first ones to show that humans are not, with the larger models, humans find it harder to distinguish between text that is model generated versus text that is written by human. So on the table on the right, you see the mean accuracy, and this accuracy corresponds to how often was the human annotator able to tell whether this piece of text was generated by a model or written by another human. So it's a binary task. And as you can see with the 175 billion parameter model, it's like 50-50. So the model is, the human is guessing as to which. So humans are starting to get confused with larger models, like, was it generated by the model or was it generated by a human, which is an achievement for these models. Because if you have tried out GPT-2, and well, it turns out that if you fine tune it, it works all right. But if you use it out of the box, it's really bad. So it's an improvement in that sense. Okay, moving forward. So this is where I feel like instruct GPT, right? Instruction following GPT. So this is the basis of like the latest OpenAI models, which people talk about reinforcement learning with human feedback and instruction tuning. So this paper essentially covered those ideas. And I'd like to go maybe a little deeper into this and explain the processes that that are explained in this paper. And uh, so let's talk about like what were the findings first before getting into the details. Like the authors showed that um, la- larger models do not inherently make better at following instructions. This means that like previously we were discovering that the performance on tasks was going up, but it turns out that there's an issue of alignment. And alignment essentially means uh, when you ask the model for something, how often does it understand what you're saying? How aligned is it to human preference per se? So you could ask the model to do X and maybe it doesn't answer. So it's not well aligned. However, when you maybe like do few shot learning or prompt it with something, it might do well. So in this paper, there are a couple of techniques that the authors introduced to enable alignment. And the first one was instruction fine tuning. So in this approach, uh, a pre-trained model was shown certain prompts, sorry, certain prompts were picked at random and they were shown to humans. So certain instructions such as summarize X could be one instruction, and then the humans had to complete the instruction. And so there were training data collected of this sort. It could be summarization, it could be question answering, it could be blah blah blah. And then the model was asked, and then using this data, which is the instruction and the human written completion, models were trained. So this is like the first step where you instruction fine tune. And then there is the RLHF part, which I think I have it on the next slide. So let's just go there. So on the right, you can see the examples of instruction. So classification instruction could look like the following is a list of companies, blah, blah, blah. And then the completion, which is written by the human, could be like, uh, uh, so Apple corresponds to category technology, Facebook corresponds to social media. What does FedEx corresponds to? And that what does it corresponds to is written or filled in by the human. So the input would be the entire prompt or the instruction, and then the output would be what human specified the completion to that prompt is. So the models were trained using instruction tuning initially, and then comes the RLHF part. So in the RLHF part, you would essentially you would first train a reward model. And how you would train these reward model is by taking the model that you have initialized or trained using instruction tuning and asking it to generate text with certain prompts. So once it generates those texts, you would ask the human. So you could change decoding parameters such as top K, top P, and other parameters to generate multiple text for the same prompts from the model. And then you would ask the humans to rank these prompts. And so using this ranking information, you could essentially generate or train a model to align with human preference. So this reward model essentially takes in a text and generates a scalar value for how preferable is this output according to humans. So if it's a good text, ideally this reward model is essentially, so the reward model is essentially a proxy to human grading. And so once you've trained this reward model in this fashion, you move on to the next step, which is fine tuning with reinforcement learning. And I guess in every reinforcement learning task, you have to define a few stuff. So the policy in this case is a neural network. The action space is what actions should be taken given a policy. And this is essentially the words in the vocabulary. The observation space is the input sequence of tokens that the model sees. And finally, the reward function of this, the reward function is framed in a way where you would want to minimize or inhibit the model from predicting outputs that deviate too much from the base model. So again, the base model was instruction fine-tuned, and then you ask, and then you would say that I'm training another model which is initialized to be the same as base model, but is further trained with RLHF. And you want to make sure that the generations from these two models are similar for the same prompt, while also maximizing this reward model's output, the scalar value. So you essentially perform an RL update on a combination of the reward for a piece of text generated by the RLHF model, which is the one on the right, and you also want to minimize the changes in weights or the updates. Yeah, sorry.
How much human feedback is needed? Thank you.
That's a good question. I haven't really explored the data sets, but these data sets are available. Like the rewards model are available on on Hugging Face. So I think it'd be a good thing to go and see it.
About 30,000.
Yeah, I would guess so, like a few 10,000s.
But it matters like the quality of inputs and outputs. So OpenAI spent a lot of time training people who were creating these instruction data sets. And that's why the output quality from ChatGPT type model is really high. Versus if you take just like a Reddit output or something like that, it's not going to be very good.
Yeah, my question is, does that scale linearly in terms of feedback? So does OpenAI?
I don't know that how it scales, but what we've seen from finding smaller models, anywhere from 50 to 100,000 samples is a good kind of, it covers a good distribution of interaction data. And so they're focusing on like conversational piece of it. So 50 to 100,000 samples is good, but I don't know like how it scales. Like I haven't seen any data on that. Now, OpenAI has kind of become closed AI, so they don't really do nothing as they used to.
Yeah. I think I'll take maybe 5 more minutes. Yeah, I can run through it.
Yeah.
Yeah.
So we can keep the discussion probably at the very end. So we have
Sure.
more.
Yeah, I realize that it's gone a bit too long. Yeah. So yeah, thank you for that. I would also insist maybe for people to go through the citations if they're interested. I mean, maybe for folks who have already read this stuff, they already know it, but folks who don't know, it might be more informative or more in detail with the mathematics of stuff. So the idea here is, again, you have models or 2 models that are initialized with the instruction fine tuning, and then you want to train one of these models with reinforcement learning. So again, the objective is to not change the model parameters too much so that it generates text similar to what it was generating after instruction tuning, while also maximizing this reward function from the reward model, which is trained to enhance the text, or which is trained to select text that is more preferable to humans. So that's the general idea. And yeah, and so some of the results was like even the smaller models trained with RLHF were outperforming the larger 175 billion GPT-3 models. And so, yeah, and even like with RLHF, it's pretty interesting because you can also control, because the reward model is biased towards humans prediction, you can also control for toxicity and bias, because the reward model would automatically give less weight or less preference to output that's more toxic or biased. There are a few more models. Maybe I just cover the ones briefly. So there is this interesting paper called Chinchilla, which observes that there is a relationship between the model parameters and the data that you use to train that model, which leads to optimal model performance. And so this paper introduced like a Chinchilla 70B model, which is roughly 4 times smaller than a preceding model called Grover, but it was trained in 4x the data and it still outperforms. So it's essentially 4 times smaller, but it does better than the larger model with more data. So there are these curves. You can see the graph on the left, which is like the isoflop curves, which essentially on the y-axis is the loss, which is an indicator of the model performance. Each curve is essentially trained with the same training flops, and the x-axis is the model size. So each curve would have varying amounts of data as the model size increases. So generally with higher model size, if you want to keep the flops the same, you would have lesser data. And as you can see, it follows a uniform structure. So this can help you predict for a given amount of compute budget that you have, which is measured in flops, what would be the optimal model size that you would want to choose, and the training data to train that model in order to get the best performance, the best bang for the buck. So it's pretty useful, because when we train large language models, we we would expend a lot of resources, and this would help mitigate some of the carbon footprint per se. Then there's a GPT-4 model that I guess there's not much in technical info on it per se about the model parameters and stuff like that. But I would just like to talk through a couple of images here, which essentially shows that these models are doing pretty well now, and they are exceeding or matching or even exceeding human performance on a lot of tasks. And I think one interesting insight is that they use the scaling laws similar to Chinchilla, and they were able to train smaller models to determine what would be the performance of the larger GPT-4 model, the bigger one, and what would given a certain compute. So that was pretty interesting. So they didn't really need to train too many models to figure out what's the ideal model parameter size that they want for a certain performance. And finally, results on lead codes for software engineers there, like maybe you still don't need to worry because the lead code hard is still, it's not there yet. But yeah, so we can just wait and watch. But yeah, I mean, there isn't much to, I would suggest, I think the risk and limitations in this paper is pretty interesting. So if you get time, you can go through the technical report. It's really not super technical, it's more wordy. So it just explains how does the model do and what are some of the concerns with these models. Finally, wrapping up, there are a lot of concerns around LLM. Here I have listed 3 of them. There are probably more, such as robustness and stuff. So first thing is lack of transparency, right? Because organizations and industries racing to train their own large language models, there is not much information available about the training data that was used. There could be potential data contamination. There's also need for standardization of evaluation of this model. There has been some progress made with papers like Helm, which talk about which is holistic evaluation of language model, which present a unified evaluation framework for large language models. There's additionally concerns around hallucination. Hallucination is when a model makes a prediction that is factually incorrect or is given the previous context, the generation does not make sense. So the generation might still be syntactically and semantically sound per se, but it isn't really attending to the crux of the question or the instruction provided to it. So these are this is a pretty important issue, I feel because you can easily get fooled when the model hallucinates, especially when large language models hallucinate, and if you're not paying too much attention to the exact details of those generations. So one example is maybe I think Stack Overflow recently had to close the ability to fill in answers with large language models because they were providing seemingly right answers, although they had bugs and were errors. So you need to really inspect the model output. And then finally, mitigating bias and promoting fairness. We all know that the internet has a lot of data and some of it can be very toxic. So how do you prevent these models from learning those implicit biases around implicit biases? And then there are some techniques to mitigate it, like RLHF certainly mitigates it. You can do data augmentation to mitigate it, other strategies, but it's still an open challenge. And with